Okay, so we're going to kind of let this spin here. And I think what we should do, as you're ruminating about the answer to this question, is talk a little bit about this quality revolution. Spur your memory a little bit. This began really in the U.S. back in the early 1980s, right? A lot had changed from 20 years before that, right? We lost our dominant position in manufacturing to a large degree, right? Semiconductors were invented in the U.S., but by 1980, about 90% of these were being produced in Japan. A large segment of Americans were driving Japanese vehicles. And it was something of a wake-up call as we were losing this competitive position that we'd once had. And there was sort of a feeling in the general public that Japanese manufacturing was producing, especially in the vehicle sector, cars that were more in tune with what customers really wanted, right? Producing smaller vehicles during an oil embargo makes sense, right? The American cars tended to be larger, right? So more in tune with customer wants. There was an impression that these vehicles were ending up in the shop less often, right? And that these companies were actually more profitable in Japan. And the watershed moment of this revolution, if we can point to one thing, was an NBC documentary, a white paper. It was called "If Japan Can, Why Can't We?" And what this documentary outlined was the differing philosophical approach to quality found in Japanese companies, right, the heavy manufacturers in particular, in electronics and in automotive, right, that differing philosophical approach to quality, and how that philosophical approach at the top levels of management could become pervasive throughout the organization, such that the whole organization could be centered around these types of concepts we've talked about already: TQM, SPC, robust design, etc. And it seemed to hit home with a lot of people here in the U.S. And next thing you know, there were requests for transcripts going into NBC, and W. Edwards Deming was invited from many directions to come back here to the U.S. and do some consulting here on these quality issues. But one thing to note about this quality revolution, it was not a technological breakthrough of any sort. It was not even the development of new methods to allow us to operationalize quality. Those methods were invented, again, here in the U.S. back in the 1920s. What this quality revolution was a shift in attitude. It was simply a paradigm shift. It was sort of a fundamental adoption of that philosophical approach which had taken root in Japan. It was a shift away from something we've called the product control approach to quality and towards something called the process control approach to quality. And we outlined it, although we didn't call it those two things, a couple lectures back. And I'll come back to that in just a minute, what we mean by process control versus product control. It was a shift away from controlling the product through inspection, right? We talked about inspection as a means to filter out bad quality before it reaches the customer. And it was a shift toward a mentality where we were removing process faults at their root cause. Right? We have that diagram up, and you see it here in your notes, where design, manufacturing, inspection, and then the customer. Inspection being used as a filter. What's wrong with using inspection as a filter? After the fact, so what? At least it doesn't reach the customer. So it costs money. Okay, that's certainly one point. So it's waste in terms of money. What else?
It's not preventative.
Well, it's not preventative, so what?
Maybe so what?
It's waste in terms of material, too, if you have to scrap whatever was wrong.
Materials, it's almost an environmental angle you could take on that as well as economic. And why else?
It just keeps happening.
Keeps happening? You think you're going to filter out all the bad product? You're using an inspection-based scheme? Talk more about that in just a minute. No way. You can't analyze every product. And if you can, your costs are going to be excessive. That's not good for the customer either. Right? So inspection was really an ingrained mentality. I'll go through the historical perspective on this in just a few minutes. You'll see why it became an institutional activity, inspection. But it was an abandonment of that as the only means to achieve quality. And certainly inspection has its place, and certainly it's appropriate in certain situations, but it should become clear when through our discussion here today. This quality revolution was also a departure from the paradigm which viewed quality as the responsibility of only one individual or one department, the quality department, right? Remember Inspector 13 from the Fruit of the Loom commercials, right? It was her job to make sure the underwear was to quality specification, right? Well, is that really a good thing, or is it really something everybody needs to be thinking about all the time? Especially if we're going to talk about a preventative approach to quality. The people in design and people in manufacturing need to be thinking about this. You can't just outsource it to the quality department, just like we can't outsource environmental quality to an environmental quality department or environmental engineers and scientists. Again, if we're going to be preventative, we have to understand our process very well. And that's come up a number of times. Right? So quality is the responsibility of everyone. And to concur with what the gentleman said in the back, right? Prevention is better than cure. Ben Franklin said that, right? An ounce of prevention is worth a pound of cure. Right? We can talk about inspection as being cure. It's exactly what it is, taking care of it after the fact. We can talk about waste treatment control technologies as being inspection prior to release, the customer being the environment. And it's the same sort of ways. And we talk about prevention, an ounce of that being quite good in terms of economics and in terms of the environment. And that's really what the quality revolution was. When we talk about product control, we're talking about is through inspection filtering out bad quality. That was the old way. The new way, centering management, design, manufacturing, research and development, marketing, all around the customer. And where faults exist in the system, removing them at their root cause. That's what we mean. We're going to talk a lot more about process control today, because you need to understand it, because it's, again, very relevant. Now, one of the issues associated with the product control approach to quality is that inspection comes late in the game. Right, and I think this was mentioned here just a minute ago. And what's the problem with inspecting late in the game? Well, you're going to find your quality faults late in the game. A lot of problems might already be out in the field before you find what the cause of the problem is, if you're even looking for it. And the costs to fix the problem go dramatically up. Right? If I launch a process and then I have an inspection down the road and I find fault with the process and it's big enough for me to do something about it, not only is it difficult to go back and find the root, but it's going to be very expensive to make changes. If we're talking about looking for quality faults during the design stage, it could be just a click of the mouse. It could be just an eraser, right? Saving all of the waste down the road from occurring, right? So it's better to find these things early. It's cheaper to find these things early, right? And the notes you're going to download from ME Online and the students in class have in front of them right now talks about an example where some consultants went out and they analyzed two different companies. Company A, Japanese company, and company B was a U.S. company. Both were making picture tubes. And they looked at the effort spent on looking for quality problems as a function of the life cycle stage of the product. And basically, company A, the Japanese company, was thinking a lot about quality during the design and manufacturing stages, and very little later towards job one as that first product rolls off the line, and very few issues of warranty coming up. Right? Recalls are very expensive. Right? That's the worst form of inspection, is your customer being the inspector, right? Or the National Highway Transportation Authority, right, being the inspector, right? And now you got to bring all these vehicles back. How expensive is that? Right? If you can, again, find these faults early, again, in a preventative sort of mentality, it's going to be a lot cheaper. And because there will always be mistakes made, right? So thinking about them early is the way to go. Now, of course, we've caught up in the 20 years since the quality revolution. But what had to happen was pushing these quality considerations backward in the life cycle, back to design and manufacturing, right? We talk about cross-functional teams now. And that's one of these buzzwords that people have a problem with. But again, if you can always take any concept too far, right? The point here is that people in design need to know something about manufacturing so that the designers produce something or they design something that's easy to manufacture such that there won't be many defects to be corrected. Right? You have to push these considerations back into design and manufacturing. Have to push them upward into management. We're going to see why that's necessary in just a minute here. But it's that TQM idea again. And laterally into research and development and into marketing. Right? Don't try to push vehicles that are very large if the consumer is demanding small vehicles, or unfortunately vice versa. A lot's changed in 20 or 30 years here. Right? But why do we need a quality revolution at all? A lot of the things we're talking about here are common sense. Why did we, for 80 years, have industrial systems that featured inspection, for instance, as a metric of quality, as a product control approach? Well, it's not too hard to understand if we take a look back, right, and take a historical perspective on this view of quality. Back before the Industrial Revolution, there were individual artisans making product, right? Suppose I make shoes. I was an artisan, and I had a shop with a sign outside the shoe maker. Okay, now you come and buy a pair of shoes from me, right? And your shoes wear out quick, they blow a hole out quick, whatever, right? What are you going to think about Skurlos' shoes? That becomes very personal, right? And you might come back with your shoes and ask me to repair them. You might give me another chance. You might not. You might go to somebody else. But the fact is, it was my reputation on the line. Very personal. Right? What happens when the Industrial Revolution comes along? You got the assembly line. Well, rather than being in control of the full product, I'm only in control of some very small part of this system. Maybe now it's my job to work on the assembly line and to bolt tires onto the front of a vehicle, right? And I do this all day long, right? Or to somehow fixture some component inside the engine. Right? That's my job all day long. It's very repetitive. Probably going to get bored, and I'm probably going to start working slower. And that's basically what happened. In fact, productivity was too low to make profits initially on the assembly line. So the gentleman called the father of industrial engineering comes along, F.W. Taylor, and says, okay, we're going to study this problem. We're going to try to do something about it. So what did Taylor do? He went and he studied how people work, developed work standards, tried to understand how long should it take somebody to accomplish a certain task. And then having some understanding, a baseline of how long it should take somebody to perform a certain task, he developed wage incentives to get people to work faster, right? Good idea. You work harder, you make some more money. But things got a little bit skewed over the year, and probably in a way that Taylor didn't intend. All right, so what happens? Well, the rise of the unions happens, right? And these work standards became tied to union contracts. And rather than providing some level of incentive, what they became was a ceiling. So if you work, or if you put into a particular contract, a work standard, what's going to happen? Well, it lays down the expectation for the workers. And suppose the quota is met for the week. What happens? Are people going to be motivated to continue to work? Well, maybe not. And this happened, and Professor DeVore likes to tell a story in his class, and I like to repeat it, where he was visiting an automotive manufacturer not too far from here. And it was around 2:30 in the afternoon or so, and he went to get a cup of coffee. He's out on the line taking measurements, SPC measurements. He goes into the cafeteria and finds what seems like the whole workforce in there, playing cards, right, smoking, laughing it up. And he was a little bit surprised, of course. And I don't remember what day of the week it was, but basically had to ask, what's going on here, right? And, of course, they'd met the work standard for the week and didn't have to work anymore, essentially, right? Is that good? I would argue not. And I'm not taking a position on unions here, but I don't see how that's good for the company. I don't see how that's good even for the workers, right? Who's that good for? Right? It's a competitive world we live in. I don't know if this practice is continuing. That was about 10 or 12 years ago. But the point should be clear, right? What happens when you take a concept, any concept, too far, whether it's TQM, SBC, or work standards. You've got to keep your head in the game, and certainly allowing that to happen isn't good for anybody. But that's essentially what happened. The metric of process performance was only the number of units you could produce per unit time. And it was an artifact from the time where people were working slow, right? But that's what became the metric. And it became so entrenched as a metric of process quality that even when better methods came along, such as Walter Schuhart's approach to statistical quality control back in the 1920s, they were largely ignored. Now, as the work standards became entrenched and productivity increased, well, what happened? Remember, we're in the product control mentality. Well, you keep producing more and more and more product, and it becomes impossible to inspect all of it. So two individuals did some good work on this, statistical work, Dodge and Romick, back in the 1930s over in Bell Labs. And they essentially developed the statistical tools necessary to be able to sample from a larger population and analyze that smaller subsample from the population and be able to infer some characteristics of the larger population. In particular, suppose I was interested in making sure that no more than 5% of my large population of products were defective, right? Maybe I've established some acceptable quality level, AQL. It says I don't want more than 5% of that product to be defective. Well, I could subsample, maybe look at 100 products instead of tens of thousands, or maybe 1,000, right? And know, okay, if I see less than 2 out of 100 parts are defective, then I can be better than, say, 95% sure that no more than 5% of that total population is defective. It gave me the tools to be able to do that, the statistical tools, the subsample. And not only did this metric of quality of units of produced per time, right, that become entrenched, but what this statistical tool allowed people to do was to entrench this acceptable quality level. Right? So it became the way it was done. Establish some acceptable quality level, subsample from the population, and compare. Right? This is a big part of industrial engineering. I know in the program that I went through, they were still teaching AQL back in the mid-1990s and even late 1990s. Right? That tool to do it. Now, there was nothing wrong with the statistics. Right? Subsampling is a very important tool. Right? But the mentality is all off. Right? You're allowing a certain amount of defect to reach the customer in essence. Right? And that just more entrenched the problem of just getting the numbers out, and that being the sole metric of process performance. Right? So Schuhart's methods were largely ignored until the Second World War. And it was interesting because World War II had it entrenched both inspection and process control. I shouldn't say entrenched it, but they tried it out. Right? There was this war production board that was in charge of converting civilian industry to military industry, right, during the war effort. And the war production board advocated Schuhart's methods of process control, right, removing defects again at the source of manufacturing. Of course, nobody wanted airplanes out in the field that were defective. Right? That's plain old patriotism. And sons of people building these things were out there fighting. Right? So there was both process control and inspection during this time. And the engineers loved the process control. It worked. Right? And they were advocated, proliferated during that time. But what happened after the war? After the war, the U.S. economy in the 50s and 60s was pretty much the only one on its feet, right, and chugging along. So we converted back to civilian production and could sell anything we could make in that time. And it was already sort of predisposed, American industry was, to get those numbers out. Get them out because you can sell it. Right? Why shut down the line? Right? The managers came downstairs during this time and see people there making charts, shutting down lines, looking for faults, right? And they thought the engineers were whacked. I said, get that line going again. Right? Their salaries were tied, in fact, to getting the numbers out. Right? You're a manager in charge of production. How are you going to give, on what basis are you going to give such a manager a bonus? Right? You get the numbers out. You're going to measure the numbers. More output, more incentive. There was no tie back to quality, no feedback loop. Didn't exist in that time. Right? So SPC sort of fell by the wayside. And folks who were very much involved with it, people like Deming, didn't have an audience in this country anymore. So what happens? Deming goes to Japan. Some of the top business leaders there welcome the idea, the notions of quality, total quality control. That's where the 14 points came from. They actually evolved over time as he was presenting this idea. He learned right there that the upper management needed to understand why quality was important. The engineers understood it. Right? SPC came first, then TQM came. Right? And these 14 points in Deming's philosophy, he was a statistician. Right? We're all about getting it to the top first, getting upper management to buy into quality first, then having the supporting tools. Right? And of course, there were other folks in Japan, people such as Taguchi, who had some very useful tools to help out on the design side, right, consistent with that sort of philosophy. Right? So, and then, next thing you know, we're up in the 80s. We lost our competitive position, and we have the quality revolution. So while the ideas seem obvious, and they should be obvious to you, you do have to recognize, to some degree, the history isn't forgotten, right? And you can sort of trace back a lot of institutional behavior to situations from history, if you will. So I think it's important to understand. Which brings us to the question now. We talk about the quality revolution. We haven't defined it. So I'm going to ask one of you to define it, to answer this question here. What is quality? Anyone? Anyone brave enough to give us a definition? Remember, we went to Webster for our definition of design, right? To conceive or plan out in the mind. That was pretty useless for us as designers, manufacturers, business folks. We talked, rather, instead of an operational definition, talk about defining and defining trade-offs and finding a balance between them. And mathematically, you can do that. Definition of quality.
A reduction in variation with type of control or standard.
Well, that's a good definition. How many people who haven't been exposed to this before would have thought that off the top of their head? It doesn't come very naturally, right? But it's indeed how people look at it now. I'll come back to that. It's the one we'll use. Has anybody heard of conformance to specifications before? Right? Used to be, for a good 60 years, if you ask somebody what is quality, the answer you would get is conformance to specifications. Parts conform to spec. Well, they're good quality product. Right? This is the way it was for a good long time. And times have changed in the 2 years, 3 years since I last taught this material, right? Because I would always get somebody who says, well, it's conformance to specification, right? And that's it's important to understand, what's wrong with this definition, conformance to specifications, right? And it's actually, when you think about it a little bit more, it's not very consistent with our intuition. Right? Suppose I've got 3 individuals and we're looking at their test scores. One of the students gets a 69. One of the other students gets a 71, and the third student gets a 95. Right? And let's say 70 is passing. Right? So what happens? 2 of the students pass, 1 of the students fails. Right? And in the old conformance to specifications view of quality, and that makes sense. It's a very useful operational definition of quality. If we're going to be inspecting stuff, what are you going to inspect it against? Right? The specifications. And if the product conforms to specifications, you let it out the door. Right? So it's a natural view of quality in the product control mentality. Conformance to specifications. But if we look at these test scores, right, 2 pass. Right? We've got 2 students conforming to specifications, and 1 that doesn't pass. That's 69 students. But is that really consistent with our intuition? Are the student who gets a 69 and the student who gets a 71, are they really that different from each other? No, it's one multiple choice question, probably random chance that 1 happened to pass and 1 didn't, right? That random noise that allowed 1 to pass and 1 didn't. Certainly that 95 student is far different from the 71 student, but we put them in the same class, right? The pass class, right? So this conformance to specifications as an operational definition, well, it isn't very useful. And I talk about operational definitions. What do I mean by an operational definition? Talking about something that we can all agree upon. And I would argue that the definition presented to us here maybe still is a little bit too complex. Right? We need to simplify it a little bit, or develop the right background so it becomes a simple idea. Right? An operational definition is not vague at all, like our definition of design. Right? Or if you look up in Webster the definition of quality, you'll find it's a characteristic or having some aspect of excellence. Right? But we also should know from our intuition that it's not just about sort of excellence, right? It's about consistency also, being consistently excellent. And what was brought up was the variation issue, right? Why do people end up at McDonald's all the time on a road trip? It seems whenever you take a road trip, you end up at McDonald's. And a lot of us don't eat there regularly, but still might end up there on a road trip, right? What is it about McDonald's? What's that? They have clean bathrooms. Yeah, well, it's consistent, right? Generally. Generally. Right, but the food also has some expectation associated with it, too. Right? There may be a better restaurant down the street, but there's some risk involved. Right? There's that consistency factor. Being consistently good. Right? And certainly the food's better than, well, I don't know the fast food chains in Michigan. We had some at Illinois, and I guess I shouldn't list them by name, but you could point to these. Well, that's good. And certainly McDonald's would be better than that one. Right? But, consistency is a large part of it, right? And we know that from experience, being consistently good, right? That golfer that consistently shoots well, right? Not that golfer at one time got a great score, right? That's the quality golfer. So, it's more than just being excellent. It's being consistently excellent, right? Getting closer to the definition that the gentleman presented here, right? Suppose, I'm talking about operational definitions. Suppose I'm talking about round. Maybe we're making bowling balls. Right? I want to come up with an operational definition of round. Right? I don't want a bowling ball that isn't round. That'd be a disaster. Not that I'm any good at bowling anyway, but you want round bowling balls. So go and look in the dictionary. Maybe it's a mathematics dictionary. What's a round? Well, what's a sphere? Right? It's a locus of points in 3 dimensions equidistant from a point called the center. Right? Remember that from high school. But is that a useful definition in an engineering sense? Where is the center of the bowling ball? How am I going to find it? Oh, and by the way, I got to break the bowling ball open to find it, right? Or do I? Maybe an operational definition of round would be take the diameter in a lot of different places and make sure they're within some tolerance, right, or some specification. That'll work just as well. It's not a textbook definition of round or, say, the dictionary definition of round, but it's something useful, something we can all agree upon. Conformance to specifications is an operational definition of quality. It's not a very useful one. In fact, it can be somewhat destructive, again, if it's taken too far. We gave the definition of test scores. Let's look at another example. Suppose you're an operator on the shop floor. You're drilling holes, and you're given a specification. The diameter of the hole should be 2 inches, and the specification on it should be 15 thousandths. Well, here's my specification limits. My lower specification limit, my upper specification limit, and the nominal. Well, suppose I set up the machine, and I'm good, right? And my process doesn't have much variation. One thing to keep in mind is we represent manufacturing processes as statistical distributions. Outcomes never exactly hit a single value all the time. There's always some spread, right? If you go far enough out in the decimal place, if you're really good. And I'm saying I'm good. My distribution is small. My variation of my process is small relative to the specification limits. And I set up the machine here. Maybe I'm at 1 in 990 thousandths or 99 hundredths. Right? And I know I'm not going to produce any parts below the lower specification limit. And we view quality as conformance to specifications. So is there any incentive for me to move to the center here, to set up my machine all again? I'm just going to crank parts out because probably my bonus is also tied to getting the numbers out. Right? What's my incentive to move to the center? Clearly, there is no such motivation built into this operational definition of quality. Again, we need another one. So, it suggests that conformance to specification is not necessarily consistent with our intuition. All right, and that's where Taguchi came in, and it's the definition the gentleman gave, we can summarize, as being on target with the least amount of variation. Taguchi did a lot of things really good in terms of his philosophical approach to quality. Right, some of his inner and outer array concepts were revolutionary. Other concepts I might not agree with. But I think this is, in my view, one of the biggest contributions of his efforts. A philosophy that the goal of manufacturing should be to minimize functional variation that reaches the customer. Right? That's a great concept because it provides some motivation to improve. If my drilling process is off-center, well, I know that I should be on target. And if I am on target, then I need to minimize the variation, right, just as the gentleman said. One other very useful tool that Taguchi brought to us was this notion of a loss function, actually quantifying the loss to the customer. Suppose I'm making picture tubes, and I'm concerned about my quality characteristic of interest is the intensity of that picture tube. And I go out and, I don't know what that intensity should be to start. Right? So what am I going to do? I'm going to go out and show maybe a number of individuals a bunch of TV sets. And I'll say, well, what is the loss to you if I produce this particular picture tube with this intensity? Right? Maybe the intensity is 12. They say, well, maybe that's too bright. And relative to this one over here, there's a loss to me of $8. Right? Or that one is too dull. It's way too dull. So I wouldn't buy that unless the price was $32 cheaper. Right? One can go about doing that and essentially map out this function, L of y. L stands for loss, the loss function. Right? And the minimum of that loss function could be perceived as the target, right? Minimizing loss to the customer. Right? Now, one thing to keep in mind is when I go ahead and make my picture tubes, maybe the design that I put together in conjunction with the manufacturing process for that picture tube, is a little bit off target, right? And remember, like snowflakes, right, there is a distribution of outcomes from my manufacturing process, right? So somehow I have to evaluate this distribution with respect to the loss function. Keep that in mind because we're going to come right back to that point. How do I do that? Certainly, if I have one picture tube that's off target, I can use the loss function to tell me how much loss for that particular picture tube. But how do I analyze the process? What is the for manufacturing with this sort of distributional characteristic? We'll answer that question in just a minute. But the loss function allows us to do that. It allows us to compare a process that's off target with less variation to one that is on target with more variation. And how would I make that choice? Loss function allows us to do that. In fact, the loss function is useful for a lot of reasons. Well, that's just one. As I mentioned, it can help us determine the nominal value for some quality characteristic of interest, right? Find the minimum of the loss function. It can help us find the right design values. If that picture tube intensity should be 10, it'll tell me which combination of design variables will give me 10. And if I further look at the manufacturing process as a function of those design variables, then it might even help me know which design variables minimize the manufacturing variation. It can help us do that too, make these trade-offs between different manufacturing processes. And it also helps us to calculate specification limits. So let's just motor through these very quickly. All right. How can a loss function help us to find a target? Well, as I basically just said, suppose my loss function can be estimated by a quadratic function. The hardest part of loss function theory is finding the form of the loss function. And this isn't a course where we're going to discuss it. But I will say that quadratic functions are used a lot. And in theory, if you're using a quadratic function, you really only need 3 points to fit it. I would never recommend somebody only use 3 points. You've got to ask a lot of people, right? And it gets into statistics, and you probably should take a course in it. But you can get the idea here easily. So suppose I show you 3 picture tubes, A, B, and C. A has an intensity, and that's Y here, of 8. The second one has an intensity of 12, and the third one has an intensity of 14. Right? And you tell me, what's the loss to you? The intensity 8, well, that's too dull. That's an $8 loss to me. Right? 12, well, that's too bright. That's an $8 loss. 14, that's way too bright. That's a $32 loss. Right? I can go back and fit the form of the function, and I can change its form to a more useful form, this ky minus nominal form, where k and nom are parameters of this quadratic function. Right? So I go ahead and just transfer this fitted quadratic equation into a different form. Right? K is 2, and the nominal is 10. It's a more useful form because it tells us exactly where the minimum of the function is. Right? Question?
Assume that you can reach zero loss.
Yes, in this form. But you don't have to. Certainly you don't have to.
Yeah.
Right? But I'm oversimplifying it here. And people might say there is no loss to me at the target. Right? But again, if you extend this theory, you'll find that it's more complicated than that, for sure. Right? So nominal is where the total loss function is minimized. Right? You can have lesser is better. You can have greater is better, like so 0 functions and infinity functions, things like that. Right? So you should just be aware of it. But the idea here is just for you to get the idea of how you can use this sort of thing. The loss function can also be used, as I mentioned, to help us find where design variables should be set. Right? And I said already, how do we trade off between being on target and achieving minimal variation? Here's process A. Here's process B. Here's process C. How do I decide between them? Right? Remember, these aren't points. We could always calculate the loss for a single outcome from a manufacturing process. But how do I find the expected loss for the whole manufacturing process? Right? It's a question. Well, it's, again, for those of you who don't do math every day, it might look complicated, but certainly it isn't. It's the mathematical concept of expectation is all it is. And what you can do is find the expected loss of this normal distribution function for this loss function. And the equation is actually very simple. I'll show it to you. Right? Here is my manufacturing process. And it has an estimated mean, mu, and a certain variation, or its standard deviation, sigma. Okay? And here's my loss function. It has a minimum at the nominal here. Okay? What I do is I take L of y, that's my loss function. It's a quadratic, right? So I can substitute that mathematical form into the expected loss for this manufacturing process. And it's going to look a little complicated, but it isn't. This is the normal distribution function, the probability density function for the normal distribution. This is a normal distribution expressed in math terms. Right? It has 2 parameters, mu and sigma. So I can stick that into the equation also. And then I can just take the integral. And I get a simple equation at the end. K and nominal come from the fitted loss function, right? Come from here. Mu and sigma come from the manufacturing process. Right? So give me a manufacturing process, give me a loss function, I'll give you an expected loss. Right? So I can now rank process A versus process B versus process C. Very useful. Yep.
Like the standard deviation of the loss?
You can. That's more complicated. It's not done very often. Absolutely. You can have all sorts of fun once you start quantifying these parameters. So here's an example. Setting design variables with this type of concept in mind. Suppose we're back at our picture tube example. And there are 3 design variables that affect the picture tube. Number 1 is how long that tube is. Number 2 is the pixel concentration. And number 3 is the glass polishing technique, A, B, or C. Okay, so I've got 3 design variables. And I have to find the settings for those variables that will allow me to be on target first, and then they're manufacturable. They have minimum variation. So how can I, in an orderly way, vary these design variables and estimate the loss? Well, that's a subject for a different day. Right? You could teach a few weeks on how to design experiments. Actually, a whole course. Now that I think about it, I taught it once. Right? Statistical design of experiments. Right? The back half of Professor DeVore's book talks a lot about these issues. How do you design experiments? I won't go into that. But here's a systematic variation of x1, x2, and x3. And I can basically set each of them at 3 levels and look at all combinations and actually manufacture prototypes. And suppose I do that, and I manufacture 4 prototypes for each. I can calculate an estimate of the mean. I can calculate an estimate of the variance. And I can go back and calculate the expected loss because I have my loss function already. Right? We just calculated. Nominal is 10 and k is 2. Right? So here's 2, here's 10, and the estimate of mu and the estimate of sigma come from producing prototypes. And I measure the intensity from these prototypes. Right? Take the average of the 4. Estimate the variance off of that average. Right? I can do that. And I find that combination of design variables that minimizes the expected loss. That's this combination. 120 millimeters, 105 pixels per millimeter square, and polishing technique B. Right? So that can really clue me in a useful way. Right? But the trick, as the gentleman up front has mentioned, is how do you get the loss function? Right? Again, we'll talk about that later, but at least you have an idea how it can be done. Surveying, getting out there, talking to the customer, prototypes, that's how you do it. Loss function can help us also set specification limits. I won't make a big deal out of this because there's other ways to calculate specification limits. But one way to do it is to take a customer perspective loss function. It'll be hard for you to see, but the nominal is here at 10, and k is 2. Okay. Now, what happens if I produce a picture tube with intensity 13? Well, there's going to be a loss to the customer. It's going to be something like $16 of loss to the customer. Well, suppose it only costs me $8 to move that picture tube close to the nominal. Well, maybe I should consider that as being outside the specification limit because I can, if I internalize that loss to the customer, because I believe in minimizing functional loss to the customer, well, then it's going to cost him or her $18. It's going to cost me $8. Right? So maybe I should do it. Right? So this one's outside the specification limit. If I produce a picture tube with intensity 11, the loss may only be $2 or so. Right? Yeah, it's $2. 1 unit off of the target times 2. Right? So it'll be a $2 loss. Well, I'm not going to rework that for $8 because I may only pass $2 along to the customer. Right? So it's a useful way to think about and get a rough idea, what good specification limits are. But again, this is another idea you can take way too far, and that's happened before too. But you get the idea how useful tuning in to the customer is. It's useful for design, it's useful for manufacturing, and of course it's useful for research and development marketing. Right? Customer focus, centering the organization about the customer. So here's a summary. You can compile a reasonable number of test results. You can estimate an average and a variation. Estimate that distribution as being normal by taking a certain number of outcomes. And of course, I'm glazing over the statistics of it. This is basically a 2-semester course that I'm presenting in just a few minutes here. Get a loss function, calculate the expected loss, right? Calculate the expected loss, and choose your design that way, right? Choose your manufacturing variables that way, right? You can do it. Now, there's only one problem here. Right? I've assumed that we can define these distributions, that these are constant and unchanging over time. Right? What happens if they're shifting? What happens if my process is out of control, if you will? Out of control meaning that the mean is moving around or the variance is moving around. It gets difficult to hit a moving target. Right? In fact, one would say you haven't even defined a manufacturing process before you can bring control. Right? If you don't have control, if you can't tell me if your process is going to break down tomorrow, how can you tell me your process is in control? How can you evaluate that process relative to these specification limits? You simply can't. If I'm a buyer, you're a supplier, and I need 500 wrenches by Friday, and you can say, well, if it's a good day tomorrow, no problem. If we have one of those faults turn up again, well, I might only be able to get you 150, so I'm only going to guarantee 150, right? If I'm talking like that, my process isn't under control, right? My mean is shifting. Something's changing, right? And there's no point in me talking about my process being good or being bad. There is no process if you can't define some statistical distribution, right? That's what process control is all about. And it's what Schuhart was really talking about. That was his central thesis, was that you cannot guarantee the economic success of a process until you have statistical control of that process. Right? You cannot guarantee the economic success until you have process control. Right? Back in the 20s, he came up with that idea. Very profound. Right? And that's what this process control idea is, as a change from this old way of looking at quality as product control. Well, what about variation? Keep talking about variation. Why is this such a beast? It's everywhere. Right? Here's my design parameters, A and B. And I set them to achieve some quality response. But I've got variation in manufacturing, variation in raw material. 1018 steel is not 1018 steel. It's not all the same. You can take a workpiece and move to different locations on that steel, even though it's a standard steel. And the hardness, the local hardness, is very different if you measure. There's much more variability in raw material than people know. And it's an interesting discovery that we figured this out in the 90s. Again, Project Professor DeVore was leading, uncovering one of these sources of variation. Suddenly, a company was getting random tool breakages. They couldn't figure out why. So the material wasn't consistent. Well, it said 1018, or whatever it was. I don't remember. But then we see this in some of my research, too. Right? Raw materials vary. Tool conditions vary. Tools become dull. Tools can be sharp, dull. Right? You can have a substitute operator working on a given day. Right? All of this is variation. And that quality response, that target, at the end of the day, when it becomes product, there's variation about that target. Put it out in the field. Plug it into the wall. Well, the power might be varying, right? From one country to the next, or one city to the next, or what have you. It could be the quality of the water. If you're making a food product or a beverage, and we're adding water. Temperatures vary out in the field, and the variation grows. And of course, the product wears out over use, aging, and not only are you just going to get variation here, you're going to get a shift in that mean response. Right? So variation is everywhere. And what we're talking about in process control is stabilizing the manufacturing process so you can define this distribution. Let's look at an example. Suppose we're machining the inner diameter of a hollow tube, and the nominal for that machining process is going to be 2.5 inches, 2.5 inches. Let's look at two sources of variation. One is a screw-up by the operator, where the operator just punches the wrong number in, and for 1 hour before the operator realizes it, there is a diameter produced here of 2.75 inches. Okay, so there's a 1/4 inch increase in the inner diameter for 1 hour. That's one source of variation. Here's another source of variation, an imperfect air conditioning system. That, it gets hot, gets cold, doesn't handle the seasons very well. Air handler keeps breaking down, like one of the buildings I know very well nearby here. leading to thermal variation in the part. Okay, again, affecting the diameter of this hollow tube. Well, what are the differences between these two sources of variation? Well, number one of them is big and one of them is small. Thermal variation isn't going to show up at the quarter-inch scale. Maybe at the thousandth or beyond, probably beyond. All right, so the degree of error. One is very obvious, one's very small. Number two here, that numerical control programming error only affects part of the product, right? That product which was produced between 9 and 10 o'clock until that source of variation was removed, right? The thermal variation is going to affect all product. Right? And the responsibility for the error is different. Who fixes the air conditioning system? Who goes in and researches this as a problem? Right? Research goes in and finds that it's a problem because it's for ultra-high precision parts. You need temperature control inside the facility, right? Not to say this would be one of those, but nevertheless. Management has to take corrective action. The numerical control error is a function of the operator, something the operator is responsible for, right? And we bring up these differences because they highlight the differences between what we call special cause variation and common cause variation. The control error is an example of what we'll call special causes. Other folks call them local or sporadic faults. It just depends on which guru you're listening to. Right? We'll call them special causes. Right? Here's what happens. Right? At 8:30, you've got a centered process, but suddenly there's this error made, and there's a shift in the mean. Right? So there's a shift in the average, or it could be a shift in the variability, sigma changes for the process. Right? It comes locally, and it's correctable locally. Could be broken tools, jammed machines, material contaminations, or drift. Right? It's said that these types of special causes are only about 15% of all variation that's out there. But it's a large change, and it's affecting the distributional characteristics of the variation. Right? Mu or sigma changes. In common causes, that would be an example, would be the thermal variation. We would call that a common cause. It's part of the variation which making up the original system. Right? It's pervasive. Right? It's part of the general system deviation. Right? And if I don't have any special causes, the mean and the sigma will be constant throughout time. Right? For 8:30, 9:30 next week and next year. There won't be any shifts in the mean or in the variation. Common causes make up this variation. Right? And it's been said that that's most of the variation. Right? It's at the system level. This motivates management to get involved because if you're centered about quality and you have a customer focus, trying to minimize variation, functional loss of the customer, and 85% of the variation can only be dealt with by management and research, right? Well, that gives you another reason to embrace this sort of TQM mentality, right? It's preventative mentality, right? So we talk about common cause variation. Only when you have what is called a constant system of common causes can you measure capability. As I already mentioned, if this mean is shifting around and sigma is shifting around, how can I guarantee the economic success of the product that's reaching the customer? I can't, as Schuhart said. Right? There is no process if mu and sigma are changing. Right? So again, a prerequisite to process improvement is process control. It's having a process, right? Getting rid of special causes of variation. Once we have this constant system of common causes, then we can measure capability. Right? And once you have a constant system of common causes, you have achieved process control. Doesn't mean you have a good process. You can have a lousy process. That's just statistically under control. Right? It's a prereq only. Right? And once you have that process under control, then you evaluate that process with respect to how well it's on target and how much variability is creating loss to the customer. Right? So we talk about process control, then we talk about process capability. How do we achieve process control? Well, that's it's a story for a different class. Let's just say that. All right, but here's the idea. Example up here. Here's a sustained shift in the process variation. Right? You've got low variation and then high variation, a special cause in the system. Right? Here's an erratic shift in the variation. Special causes showing up once in a while, affecting the variation. Here is a change in the process mean up in the upper right here. Erratic shifts in mu. None of these processes are under control. Right? Only in the lower right corner here do you have a constant system of common causes. Right? And a control chart is about mapping out this distribution, turning it on the side, looking at the distributional characteristics of your manufacturing process over time. Okay, I know you're hungry for more and you want to know how to do it. I'm only going to give you 2 slides on it. All right? What can I do? I can take a bunch of product, maybe 5 samples from a manufacturing process if it's a continuous process. I can take the average. Something out there called the central limit theorem says that that average shouldn't be too badly represented by what's called a t-distribution, something very much like a normal distribution. Okay? So to oversimplify this for our target audience here, what we're doing is we're taking averages from the manufacturing process. And those averages should follow a normal distribution, roughly. Right? It should look like this. And the center of that is the average of these averages. That's our estimate of mu for the process. Right? So not too hard to think about. We're turning these distributions on their side and sampling to do this in a very practical way. And how you establish your reference distribution, all that's is a little much for 5 minutes. But you get the idea. Right? You're just sampling over time, and a certain percentage of the outcomes should be between plus or minus 1 standard deviation. About 68% should be in this first zone. About 95% should be within plus or minus 2 sigma. And a 6 sigma process, plus or minus 3 sigma. Right, about 99.73%, I think, 6 sigma. Right, so 1 in 500 or something like that, chance of there being an X bar, an average, from our manufacturing output outside of these limits here. And generally, control limits are put at plus or minus 3 sigma, such that it's very unlikely. If you see a manufacturing output, an average of 5 samples, for instance, that is way up here, that's very unlikely. Again, something like 1 in 500. I should have looked the number up before I came. That's a 99.73% chance, I think, that it isn't there. Right? So, you're probably not chasing a fire. If you see a point up here, something's wrong with the system. There's a special cause there. And you go and you take a look at the process. You immediately can do this if you're doing this online, right? So I go and I look, what happened? What happened to the process? Oh, a tool broke. Okay, I go fix a tool and reestablish the control. Right? See, it's a very practical way to do this. And there's other rules besides just being outside of these control limits, right? If you don't see 68% of the points in the middle, right? So, for instance, suppose I see 10 in the row above the center line over here, right? What are the odds? If this is a random distribution, that's the same thing as saying I flip a coin 10 times and I see heads every time. That's very unlikely. 1 over 2 to the 10th, right? Very unlikely. So, I can come up with these other rules, right? So it's not just being outside the limits. So, we look and we say, all right, we're taking these observations and we don't really see much going on. Oh, here we got one above the control limits. We presume in that case that the mean is shifted upward. Can you use statistical process control in environmental applications to monitor pollution, in a pollution prevention application? You can. And if you read Environmental Science and Technology in December, you can look at an example. It's actually briefly described, but there's a more lengthy discussion of that work by Professor Thurston down at the University of Illinois. So anyway, you can get an idea how this connects in very directly to environmental protection. Oh, and here's what the charts look like, right? So here's a process out of control, right? Then I bring it into a state of control, and then I improve it, right? And that's the idea. Control versus capability. Control limits have nothing to do with specification limits. They are completely separate. Control means that this process is chugging along, has a certain mean, has a certain standard deviation. As I said, it doesn't mean it's a good process, right? You could be making not a single part within the specification limits, right? As we mentioned, you need to have control, and control limits help you establish control before you can start specification limits. Now, I already mentioned one way to measure capability of a process. Here's another. It's called the CP index. This is used for a long time. Right? I don't know if it's still being used or not. It doesn't make any sense to me, because all it does is you take your specification limits now, and you compare the variation of the process as estimated from your process control. Right? So sigma comes from your manufacturing process. The specification limits come from what the customer needs. Right? And you compare them. Right? So here's process A, and here's the variation of process A. And I compare that variation to the distance between the specification limits. And I get a CP value. And generally, when CP is greater than 1, it means that's a quality process. Right? People have used CP that way. Right? It means that you have roughly a 6 sigma process. Right? Or do you? Here's a process B. It doesn't have a single part, or let's say the probability of hitting the specifications with process B is very low. Nevertheless, if you take CP, it's just as good as process A. Right? CP doesn't account for where your mean is. Right? It doesn't make much sense to me. Right? No penalty for being off target. Not consistent with Taguchi's philosophy. Here's what's called the CPK, and it's a little bit more complicated, but the point is it does account for the mean. But what it doesn't do is it doesn't penalize variation directly, right? In the sense that it doesn't really help me decide between A and B, right? If I am on target with more variation, I can get the same CPK value as if I am off target with less variation. Right? Nevertheless, it's certainly a lot better than CP. And you can't do any of this, again, without process control. Well, why not go back to the customer, right? We've already introduced this, right? And I wouldn't call this a common index of process capability. But the expected loss of the customer could do that. We've already talked about how it can be done, right? But the moral of the story is you need process control first. Right? Hopefully this will get some of you interested in some classes you might not have thought you were interested in. But it all relates. Right? Suppose you're out there on the rooftop of a building taking emissions measurements. Right? Can this be used? Of course. Right? Oh, suddenly now I've got this slug of pollution coming through. What's going on? Right? Go down to the shop floor, log it, find out what's going on. You can do the same thing. Well, it's not unique to a manufacturing process or manufacturing quality characteristics of interest, such as intensity of picture tube. Right? Okay, so we talked about this idea of to be good to the environment, one must be very good at production. And this is a summary of those concepts which people are using to bring quality into design and manufacturing, coupled with TQM and Deming's 14 points. And I included in the notes a supplement of things I would normally like to talk about but probably don't have time to talk about. And actually, on accident, I took an excerpt of a reading you already had, but there's just a couple pages on that, comparing TQEM and TQM. There's also here a list of Deming's 14 points. So you don't have much time to talk about. That would take a whole lecture to go through. What's that? It was? Oh, it was there? And also the environmental version of it. Right. Okay. Was Covey in there? Okay, good. Good. I think that's pretty important. And we talk about being proactive. The 7 habits of highly effective people. That's another lecture for another day, right? But some really important things that come out of that book that are related to quality, right? This idea of responsibility, right? The idea to control your response. We can outsource the environmental issue. We can say, well, this is a government problem, it's not my problem, right? And maybe even get away with it, but is it really improving matters, right? What does being proactive mean? How do you achieve success? Well, you have to have a goal in mind. Do we as a nation have a coherent set of environmental priorities? And further, do we have a consistent set of environmental priorities that are useful on an industry-by-industry basis? Absolutely not. How are we ever going to improve if we don't set such priorities? And again, our friends in Europe and Japan are way ahead of us in that regard. And, you talk about the 7 habits. I know everybody knows put first things first, right? That's why people are generally interested in knowing what's going to be on the exam, what's going to be on the homework, rather than just trying to learn some stuff, right? Is this going to be on the exam? It's a good question. I don't know. But putting first things first, we know how to do that, right? But you have to have that goal set. And I would make an argument that we don't necessarily have that goal. And it's going to be up to our generation to establish those goals. Again, on an industry-by-industry basis. And it won't be an easy thing to do. I'm going to change gears, but I want to answer any questions if you have any. No questions? Okay.